Hello everyone. In this video we're going to learn about the set of complex numbers. The largest set that we've studied so far has been the set of real numbers, but today we're going to learn about a set that transcends the set of real numbers, and in fact it contains it, and that's called the set of complex numbers. Before we actually formally define the set of complex numbers, we need to remember a couple of things. If you recall the square root property, it said that if x squared equals k, then x can only be one of two numbers, either positive or negative square root of k, because as you know, if you take positive square root of k and square it, you get k, and if you take negative square root of k and square it, you also get k. So those are the two possible solutions for the equation x squared equals k. So if we try to solve the equation x squared equals -1, and we notice here there were no restrictions on the value of k. So if we apply the square root property here, we'll get x equals plus or minus square root of -1. Now this is a number that until now we've simply said is not a real number. If you recall in our previous videos, I always made a point of saying make sure you don't say it's undefined, because it is a well-defined number and it does exist. It just is not a real number. So, but it's a number that has some great applications to various areas such as electronics, and most significantly to Einstein's theory of relativity, for example. Without it, the theory of relativity wouldn't have been possible. So this new number, the square root of -1, which we know is not a real number, but we will give it a name and we'll call it, obviously if it's not real, a good name for it would be imaginary number. So it's actually called the imaginary number, and we call it I, lowercase I. Sometimes in electronics, because they use I for current, they use the letter J. So in case you ever see J being used for the square root of -1, that's okay too, and possible. So let's go ahead and get kind of familiar with I by first looking at some powers of I. Now obviously if we just look at the first power of I, just like the first power of any number, it's just going to be itself. So for I to the power of 1, we just have I. Now if we look at I squared, that means we're going to take the square root of -1 and square it. And of course, the rule that says the square root of any number squared is itself is universal and applicable even when the radicand is negative. So here we're just going to get -1. I cubed, think about it as I squared times I. So we know I squared is -1, so we get -1 times I, so that's going to be -I. I to the 4, we can always think of it as I squared squared. So I squared from here we know is -1. So we can say that's -1 squared. Let me write that better. -1 squared. So we know that's going to become 1. So the interesting thing is that from here, things just repeat. Let's, for example, look at I to the 5. That's going to be, you can think of that as I to the 4 times I, right? And we just saw that I to the 4 is 1. So that's just going to be 1 times I, which is I. So we're back to I. I to the 6, you can think of it as I to the 4 times I squared. So we know that I to the 4 is 1, and we know that I squared is -1. So it's 1 times -1, so it's going to be -1. Notice we have already seen that. I to the 7, you can think of it as different types of situations, but let's look at it as I squared cubed. That gives us I to the 6, right? Times I. Now we know that I squared is -1. -1 cubed is going to be -1 times I is going to give us -I. I to the 8 you can think of as I squared to the 4 or I to the 4 squared. Either way, I to the 4 happens to be 1. It's an easier number to work with, so we get 1 squared, which is 1. So, and this goes on ad infinitum. You're not going to get any new powers of I. These 4 powers of I that we've listed here in this table are the only powers of I that exist. So when you look at any other higher power, it's going to end up being just one of these 4 results. So you start with I, you multiply it by I, you get I squared, again by I, you get I cubed, and I to the 4. And from there, it's just going to cycle. That for this reason, we say that these 4 numbers here, these 4 powers of I, or these, doesn't make any difference, they're the same thing. They form a cyclic group because of this situation of order 4. So that's something you may explore later if you go into advanced algebra. So let's see how we would handle higher powers, like say I to the 42. Well, the easiest way to approach that is, if this happens to be an even number, then just go ahead and write it as some power of I squared. So here we can see we can write it as I squared to the power of, what will I need? Well, 2 times what gives me 42, right? And we know that's 21. So notice we end up with -1 to the power of 21. Now we know that -1 to any even power is going to be 1, and any odd power of -1 is going to be -1. So here we know that we're just going to end up, because this is an odd power, we know we're going to get -1. And that's it. How about I to the 100? Well, again, I squared can be used here because 100 is even. So we're going to write this as I squared to the power of 50. Now that's -1 to the power of 50. And we know that -1, an even power of -1 is going to be 1. So we end up with 1. How about I to the power of 203? Well, that's not even. I can't just write it as a power of I squared, but I look for the largest even number that's less than or equal to this number, and that would be 202. So I can always write this as I to the 202 times I. Now I to the 202 is an even power of I, so I can write it as a power of I squared. What power? Well, that's easy. Just divide 202 by 2, you get 101. So you get to the power of 101. So that's going to be -1 to the, and we need times I, of course. Let's not forget that one. We have times I. So it's going to be -1 to the power of 101 times I. Now, -1 to the power of 101, that's an odd power of -1. So that's just going to be -1 times I, which is going to be -I. Okay, so definitely try to do it I to the 1001 on your own before you come back to see what we get. All right, so we'll come back. I think you realize we can write that as I to the power of 1000 because that's the largest even number less than or equal to 1001. times I. Now I to the 1000 we can write as I squared to the power of, what's 1000 divided by 2? That's right, 500 times I. So that's going to be -1 to the power of 500 times I. We know -1 to the power of 500 because 500 is even. It's just going to be 1. So we have 1 times I, which is I. So that's how you handle these larger power of i's. Notice that none of them ended up a result different from any of these numbers. We only get those numbers. Of course, I itself is the square root of -1. Okay, so make sure you don't make the mistake, which is common. Sometimes students think I is -1. I mean, why would we give it a whole new name and all that if it were just -1? The interesting thing about I is that it's the square root of -1, a number that until now we had no real definition for. So this is already very basic, but make sure you understand it before we proceed. Okay, we are now ready to go ahead and define the set of complex numbers. And the reason we had to define I first is because the set of complex numbers utilizes I in its definition. So as you can see here, we formally define it as the set of complex numbers being C. We use this special C so that when you see it, you realize it's not just any C, but the set of complex numbers itself. And it's defined to be the set of all numbers of the form a plus bi, such that a and b belong to the set of real numbers, and I is the familiar square root of -1, which we just defined in our previous screen. Now, in the case of real numbers, we usually use the letter X to represent variables. With complex numbers, we use the letter Z. So if Z is just a typical complex number of the form a plus bi, we call A the real part of Z, and we write it as RE parentheses Z, and we call B, without the I, the imaginary part of Z. To graph complex numbers, we're going to need more than just a line, right? So this looks familiar. It looks like the Cartesian coordinate plane, but if you notice, there's a subtle difference. Here, the horizontal axis is still the x-axis, which we call the real axis, but notice the vertical axis here is no longer just y, but it's y times this I, which is the square root of -1. Multiplying by I has a quality of rotating a real number by 90 degrees graphically. So basically here, when you look at a point in this new usage of the familiar Cartesian coordinate plane, it's no longer an ordered pair, and the plane is no longer called the Cartesian coordinate plane. The plane is called the complex plane now, and a point represents a single complex number, a plus bi. We have the real part represented here by a, and the complex part times the imaginary part times I right here represented by bi. You put the real part and the imaginary part together and you get the entire complex number. So when you see a point there, that's no longer an ordered pair, but a single complex number. That's how you graph these new numbers that we are learning about. So let's go ahead and take a look at a few examples, and in these we're going to go ahead and specify the real part and imaginary part of each of these numbers, and then we're going to go ahead and graph the number. So for the first one, you can see that the real part of that number is 4. The imaginary part of this z is 3. And of course, to graph it, we would graph it like we normally would graph the ordered pair 4, 3 in the Cartesian coordinate plane, but we're going to do so here in the complex plane. So we'll go ahead and start at the center, and we'll go 4 units to the right, Then we'll go up 3 units, and we'll go ahead and plot a point, and we'll label it 4 plus 3i, like that. All right, for this next one, we can see that the real part of z is -6, and the imaginary part of z is -1. Even though we don't see a 1 there, of course, it is assumed to be a 1. So remember, the imaginary part of z does not contain the I. It's just the constant that's the real number that's multiplied by I. So to graph it, we're going to go ahead and start at the center again. We'll go 6 units to the left and 1 unit down. So we'll go 1, 2, 3, 4, 5, 6 units to the left, 1 unit down. We'll plot our point, and we'll go ahead and label it -6 minus I. This one here, the real part doesn't seem to be there. In fact, it doesn't seem to fit the bill, but of course it does, as long as you go ahead and realize that a can always be 0. So we'll go ahead and rewrite this one as 0 minus 5i, so that we have it in the standard form. Of course, if you really want it in standard form, you could go ahead and write it as 0 plus -5, like that, times I, if you want it to be in a plus bi form. But that's an unnecessary step. When we see this, we realize that the real part of z is 0, and that the imaginary part of z is -5. So we'll start here again. This time we don't move left or right because the real component is 0. So we'll just go down 5 on the imaginary axis yi, and we go 1, 2, 3, 4, 5. We'll plot our point, and we'll go ahead and label it -5i. When this happens, in other words, when the real part of a number is 0 and it lies entirely on the imaginary axis, we call such a number pure imaginary. All right, so this last example, again, this doesn't quite look to fit the bill, but I think you know the drill now. It is a complex number, but its imaginary part this time is 0. So we're going to write it as z equals 3 plus 0i. Notice that the real part of z is 3, and the imaginary part of this complex number is 0. So to graph this, we just start here and we move 3 units to the right and stop, because there's no imaginary component. So when this happens, of course, we'll just label it 3. And when this happens, this kind of a number is a familiar, good old real number. You don't need to say pure real, of course, because we're already familiar with real numbers. And that's basically the definition of the set of complex numbers. Now, as you can see, this can be done with any real number. So this tells us something interesting, that all real numbers are also complex numbers whose imaginary component is 0. So this means the entire set of real numbers is in fact contained within the complex plane, and therefore is a subset of the set of complex numbers. And visually that's completely clear, because here's the set of real numbers. Of course it's contained in the complex plane. So of course the way we say that, using a subset notation, we say R is a subset of C. But of course we already knew that R itself has some subsets. For example, we know that the set of rational numbers is a subset of R. Those are all the well-behaved fractions that can be written as one integer over another, where the denominator is of course not 0. And we know that rational numbers themselves contain the set of integers which contain the set of whole numbers. Integers are of course all the positive and negative whole numbers, the whole numbers and their opposites together with 0. And that of course contains the set of counting numbers or natural numbers, n, which is just the ones you can count on your fingers, 1, 2, 3, 4, etc. So this nested relationship holds for all the sets that you've studied until now, except for one. Notice there's one set that's missing, the ones that don't play like the others do, right? The ones that kind of like behave a little bit irrationally, right? And they're exactly called the set of irrational numbers. They are not very tameable numbers. You cannot write them as a quotient of two integers, and even if you write them in decimal form, they're not very well behaved. When it comes to rational numbers, even in decimal form, they're very well behaved. Their decimal forms are either going to repeat or they're going to stop at some point. With irrational numbers, if you write them in decimal form, they neither repeat nor do they terminate. So we need one other relationship when it comes to subsets, and that is that the set of irrational numbers, which we usually use P for, is contained in the set of real numbers. Of course, we know that irrational numbers are real, and that is contained in the set of complex numbers. So here is the relationship of all the sets that we've studied to date. Make sure that you understand these basic facts before we proceed. Okay, so before we start doing any operations with radicals, it's extremely important that we understand a generalized version of two rules we're already familiar with, one being the product rule for radicals and the other being the quotient rule for radicals. Previously, when we saw these, we always made the stipulation that square root of x and square root of y should be real numbers for this to be true. Now that we have learned about complex numbers, we can actually loosen that requirement, but we have to add a new requirement. So we no longer need to say as long as square root of x and square root of y are real numbers, which basically just meant no negatives under the radical. But instead of that, we're going to say only if x and y are not both negative, because the rule will not work if both of these numbers are negative, as you will see in a minute why that happens to be so. And however, another familiar rule from the past which we've studied, which is take the square root of any number and square it, you get the number itself. This is preserved. This is true for all x, whether x is positive, negative, or 0. So it's nice that we still have this familiar rule that's going to be working no matter what the radicand is. In the rest of the problems that you see on this page, we're going to be simplifying, but we have to keep in mind what we mean by a simplified radical expression. Basically, you want to leave no perfect squares under any radical, you want to leave no negatives under any radical, and you want to leave no radicals in any denominator. Those we'll of course see a little bit later, but I just wanted to put all of those together because when it comes to radical expressions, this is what we want to aim for when it comes to a simplified expression. So now let's go ahead and take a look at this first example, and you can see we can go ahead and apply this rule from right to left and break this up as the square root of 36 times the square root of -1. Of course, we can do that because they're not both negative now. See, one is positive, one is negative, so we satisfy the rule. So of course, square root of 36 is 6, and we'll go ahead and rewrite square root of -1 from what we just learned. We know that that is I, and that's how we're going to leave the final answer. For this one, we're going to go ahead and break it up as the square root of 28, or better yet, we're going to try to break it up into 3 parts. We'll put the perfect square part in the first radical, the non-perfect square part in the second one, and we'll leave the third one just for -1. So 28, as you know, if we look at the prime factorization, it gives us 2, 14, 2, 7, 7, 1. So there is in fact a perfect square hidden inside 28, which is 4. So we'll put 4 in the perfect square radical. We're left with a 7 that's going to go in the non-perfect square radical, and we made a new radical just for the -1. So notice that 4 times 7 times -1 is indeed -28. So again, we've used this rule going in this direction. So now we end up with 2 radical 7, and of course, instead of radical -1, we're going to write I. So when we say no negatives under the radical, we mean make sure you separate them and then turn them into an I at the end, like that. All right, so definitely you should try the next one on your own before you come back to join the video. And welcome back. So 500, if you know what the largest perfect square factor of it, then you can go ahead and just say it. If you don't, we'll go over how you can get it with prime factorization. But I think you realize it's pretty simple. The perfect square factor of, or the largest perfect square factor of 500 is indeed 100, right? And we have 5, and we'll make one radical just for the -1. So now we're going to get 10 radical 5 times I. And that's going to be our final answer. Now, if you don't see this 100 very easily, aren't as comfortable with numbers, you can always do the prime factorization of 500. Start with the smallest prime number that goes into it, which is 2. Divide and you get 250. Ask the same question again, what's the smallest prime that goes into 250? And that's 2 again. Divide, you get 125. What's the smallest prime that goes into 125? That's 5. Divide and you get 25. Again, 5 gives 5, and another 5 gives 1. Once you hit this 1, you're done with the process of prime factorization. And we notice here we have that's a perfect square and that's a perfect square, and of course the product of 2 perfect squares is also a perfect square. So we have 4 times 25, which we know is 100. Or of course we could write them as 2 squared times 5 squared under the perfect square radical. Or we can write 100, and we end up with the same number. So in case you were wondering how we got the 100, there you go, no problem. All right, so make sure you can do these simple problems before we proceed. All right, so let's go ahead and look at a few more examples here. And on this first one, notice that this negative is on the outside of the radical. So we're just going to carry it. And we can go ahead and break up the square root of -144 as the square root of 144 times the square root of -1. So of course we get -12i. All right, for this next example, you want to make sure that you don't multiply under the radical because the index is even and both of these are negative. So we are not ready. So let me write just the square root case of that. The square root of x times the square root of y equals square root of xy as long as not both x and y are negative. All right, so what do we do when they're both negative? Well, there's still something that can be done. We just deal with them one at a time. I can take the square root of -7. That I can write as the square root of 7 times square root of -1, which is fine. And this one, I can do the same. So I can write it as the square root of 2 times the square root of -1. So now the square root of 7 and the square root of 2 I can use this rule with, because of course this rule works if they're both positive. So we get the square root of 14. Now we know this square root of -1 times this square root of -1 is just going to be I times I. So that's square root of 14 I squared. Now if you remember, I squared is -1, so we get square root of 14 times -1, or just negative square root of 14. So you have to be very careful when dealing with situations where both radicands are negative. You have to handle it in this careful manner. All right, so we know that we have to do the exact same thing again because both of those are negative. So here we end up with square root of 4 times the square root of -1 times the square root of 100 times the square root of -1. And of course that's 2i times 10i, so we get 20i squared, which is 20 times -1, so we end up with -20. Now this next rule, and in fact the very reason why we created this new restriction that they shouldn't both be negative, was actually to preserve this property that the square root of any number squared is itself. Now this rule is universal. You can always safely use this, so it'll work out in this case too. Watch, because you get square root of 26 times square root of -1 times another square root of 26 times the square root of -1. We know the square root of 26 times square root of 26 is just going to be 26. And then we have I times I, so we get 26i squared. We know I squared is -1, so we get 26 times -1, which is -26. So notice we could have simply said the square root of -26 squared. We could have gone from this to this. And then, since that rule is universal and it works for all values of x, we could have just said, oh, that's just -26, and we could have bypassed doing all that. But that's only when both radicands are exactly the same, which that rule can be used. All right. So with the quotients, we have the same situation. So before I actually go ahead and use the quotient rule for quotients, I'll go ahead and split those up. So that'll be square root of 300 square root of -1 over square root of 100 times square root of -1. Now remember, square root of -1, I is a number like any other number. So all the things such as cross canceling, etc., they work with I too. So here we can actually go ahead and cross those out, and we end up with square root of 300 over square root of 100, which we can now go ahead and bring under one radical if we like that. So we can write it as square root of 300 over 100, which is of course just the square root of 3, like that. So In this next one, we'll do a similar thing. We get square root of 320 times square root of -1 over square root of 64 times the square root of -1. Notice that these will cancel out, and we end up with the square root of 320 over 64. Now the square root of 64 is actually a nice number, so in fact what we could have done is the following. Let's try this again instead. This can work what we were about to do, but this will be more efficient. Since the square root of 64 is already a nice perfect square, let's leave it alone. So we just get 8 on the bottom. We'll go ahead and just break square root of 320 in its perfect square and non-perfect square factorization. So how much of 320 is a perfect square? Well, let's take a look. 320, let's go ahead and break it up into its prime factorization. Okay, cooperate here. Let's try it one more time. Well, all right, that's 3, as you know. So we know 2 gives us 160, 2 gives us 80, 240, 220, 210, 25, and 5, 1. So we can see perfect square, and 1 more. So 4 times 4 times 4 is 64. So we get 64 in the perfect square radical, and we have 5 that's left over. So we end up with 8 radical 5 over 8. And of course, we can go ahead and cancel those. So we end up with square root of 5, like that. So that's how you can simplify that one. Definitely try the next one on your own before you come back and unpause the video. All right, so here the square root of 80, -80, we can break up as the square root of 80 times the square root of -1 over square root of 5. Since these two radicands are both positive, we can go ahead and apply the rule that says square root of x over square root of y equals square root of x over y. So we can say that's the square root of AD over 5, and then we're going to have I. Now 80 over 5, I believe, is 16. So we get square root of 16i, which is of course just 4i. And that's how we simplify those. Again, please write this down on a blank piece of paper if you haven't done so already. Make sure you can do these before we move forward. Okay, so next we're going to look at combining, which is adding or subtracting complex numbers. And that's the simplest thing there is when it comes to complex numbers, because all you have to do is go ahead and combine the real parts and then also combine the imaginary parts. So the first thing we'll do is we'll go ahead and get rid of any unnecessary parentheses. We notice that the first set of parentheses are just placeholders, not doing anything. And since that's a plus, you can imagine a 1 there, and you distribute that, that's not going to change anything. So these parentheses are also redundant actually. So we can drop all of them. So we just get 5 plus 2i minus 8 plus 10i. So now we'll just go ahead and combine these real parts, and we'll also combine these imaginary parts. So we end up with We know that 5 minus 8 is negative 3, and 2i plus 10i is going to give us 12i. So basically we're combining like terms is what we're doing, and that's what we end up with for the final sum. Now when we're subtracting, of course we have to be a little bit careful, because while the first set of parentheses is redundant, the second pair is not, because there's a negative here, so we have to distribute that, which is going to change those signs. So we'll go ahead and drop the first set of parentheses to get negative 15 plus 7i. Then we'll go ahead and distribute the negative 1 to get plus 11 plus 3i. Now once again we'll go ahead and combine the real parts here, and also combine the imaginary parts. So we end up with negative 4 plus 10i, and that's all we have to do. Notice we always write our answer in a plus bi form, okay? Even if it's minus, doesn't matter, it's the same thing. You write it as, like if this were negative, you would just write it as negative 4 minus 10i. That's considered standard form for all purposes. Moving on to this next one, we notice that we have some fractions that makes no difference. We're going to do the same thing. We can drop the first set of parentheses, so we get 3/4 plus 1/2 I. Now we're going to distribute the negative, so we get minus 5/6 minus 1/3 I. So let me go ahead and put the like terms next to each other. So we're going to combine 3/4 minus 5/6, and then we'll go ahead and write the 1/2 minus 1/3 like that together, and we'll factor out that I. So for the first two fractions, we need a common denominator of 12, which means, of course, we're going to have to multiply this 4 by 3 and do the same on the top, and this 6 by 2 and do the same on the top. So we end up with 9 minus 10, which, as you know, is negative 1. And for the next group, we're going to need a common denominator of 6. So that's going to require us to multiply the 2 by 3 and do the same on the top, and the 3 by 2 and do the same on the top. So we end up with 3 minus 2, which is 1, and we get 1/6 I. So that's basically the final answer. Let me just write it in a slightly more pleasing manner. So we'll write it as a plus bi, so plus 1/6 I. And that's how you'll want to leave your final answer. So again, very simple. Just be careful with the arithmetic as always. Okay, now let's look at multiplying complex numbers. And that's actually quite simple too, because we can multiply them exactly the same way that we multiplied polynomials. We use the same kind of skills. So for example, in this first problem, we can just multiply the 7 by the 10 and get 70. And of course, I times I will give us I squared. Now we remember that I squared just means square root of negative 1 squared, which of course is negative 1. Because remember, this rule works for all numbers. No matter what x is, positive, negative, or 0, this rule holds. It's universal. So square root of any number squared is itself, regardless of what the number is. So of course here we're going to replace I squared with negative 1. So we get 70 times negative 1, and here we get negative 70. Okay? Now, Same thing for the next case. We'll multiply -7 by -9, which of course gives us positive 63. And then I times I is I squared. So we get 63 times -1, and we end up with -63. Once again, it's a negative answer. All right, so now we have one term times a sum. So of course, the distributive property is going to kick in, and we're going to have to distribute that 3i by both of those numbers. So we get -24i plus 21i squared. Be careful about the times that you end up with a square. Now, we know that I squared is -1, so we can go ahead and say this is -24i plus 21 times -1. Now 21 times -1 is -21. Since we want to write our final answer in standard complex form, which is a plus bi, we'll go ahead and put the -21 first, then we'll put -24i. And there's our final answer in standard complex form, a plus bi. Now here, we're multiplying two expressions. Each has two terms. So just like we did with polynomials, we're just going to do distribution one at a time. First, we'll distribute the 2. When we're done, we'll distribute the 8i. And then we'll just combine any like terms that may result. So distributing the 2 first, like this, and then we'll distribute the 8i like that, and then we'll see what happens. So when we distribute the 2, we get 8 minus 14i. Now we're going to distribute the 8i, so we get plus 32i minus 56i squared. Now, let's save a step and just remember that this I squared is going to be -1. So this will save us from having to rewrite the whole thing twice. So basically what we have is we have 8 minus 14i plus 32i. Negative times negative here will give us what? Plus. So we get plus 56. Now we'll go ahead and combine these real parts right there, and we'll also combine these two imaginary parts of the complex number, and we get 8 and 6 is 14, so 64 plus 14 from 32, I believe, is 18, so plus 18i, and of course plus because the 32 is larger and it's positive. So there's that. So that's how you do that one. Now for the problem like this, you can also use that little table that I showed you how you used previously. So you could have done this as well. Let me open some space here. You could have made yourself a table. This is also very nice because it keeps all the items kind of close to each other. Let me make it larger. What you do is you put one of those expressions like this vertically, put the other one horizontally like this. Doesn't matter which one you put where. Now just go ahead and multiply it like a times table. See? So you get 2 times 4, 8. 2 times -7i is -14i. 8i times 4 gives us positive 32i. And 8i times -7i gives us -56i squared. We know that I squared is -1, so -56 times -1 is going to give us a positive 56 in this cell. Now we notice that those two are like terms, and so are these two. So then we can combine 8 and 56 to get the 64, and the 32 and the minus 14 to get the positive 18i. The nice thing about this little table method is that everything stays pretty close to each other, so it doesn't get all spread out. But it's a matter of preference. Either one is fine. So for this one, of course, we're going to want to remember a rule from when we studied polynomials. And remember, or we could, of course, use the table too, like we used down there. So either way, we'll do it both ways. How's that? So we have f plus l squared. Remember, the rule was f squared plus 2fl plus l squared. Here, the actor playing the role of f is 8, and the actor playing the role of L is 9i. So we get f squared, so that's basically 8 squared plus 2 times f, which is 8, times L, which is 9i, and then plus L squared, 9i squared. Just make sure you don't say 8 squared plus 9i squared. That's the most common mistake in algebra, probably. Oh, this unwieldy page, let me fix that. Okay, so we're back. This whiteboard is not as cooperative as the real one in the classroom. So, okay, here it goes again. So we get 9i squared. All right, so now we're going to clean things up. So we get 64 plus, now 2 times 8 times 9. So that's 72 times 2, which is 144i, plus 81i squared. Of course, we know that's going to end up being -1. So basically we have 64. Let me put that -81 next to it, and then plus 144i, because remember, positive 81 times -1 becomes -81. Now 64 minus 81 is going to give us, let's see, 4 from 11 is 7, and 6 from 7 is 1, and because the 81 is larger, we get negative, so -17 plus 144i. And that's how you do a problem like that. Now, for this next one, I did promise I was going to do it for you in a table too. Let me go ahead and erase this, now that we know how to do that, and do it up here. So of course we could have used the table there. So remember, we're not doing this anymore. All right, so we have 8 plus 9i, 8 plus 9i, so we can just multiply it out like this. So 8 times 8 is 64, 8 times positive 9i gives us plus 72i, 8 times positive 9i gives us positive 72i again down here. And in this one we have positive 81i squared. We replace the I squared with -1, so it becomes -81. So of course we notice that this term and this term are like terms, and that was a negative 81, don't mistake it for less. And we also notice that this term and this term are like terms. So again, we can combine those to get the negative 17, and we can combine those to get the 144i. So in case you forget this formula, it's by no means the end of the world. Just multiply it out, no big deal. For this one, it's strongly recommended that you do know the right formula and that you do use it, because this has a lot of applications in mathematics that you need to be aware of. And so for that, if you remember these two expressions, because they involve the exact same terms except for the operation between them being different, one is positive, one is negative, one is addition, the other is subtraction, they're called conjugates. And if you remember, when you multiply two conjugates of the form f plus L times f minus L, you're always going to end up with a difference of squares, which makes these very, very simple problems, because here your f is going to be 4 and your L is going to be 8i. So you're going to get 4 squared minus quantity 8i squared. Make sure you're squaring the entire 8i. So here you're going to get 16 minus 64i squared. Now we know that I squared is -1. So that's 16 minus 64 times -1. So that's 16 plus 64, which is actually just 80, which is a real number. So notice what happens when you multiply two complex conjugates. You end up with a real number. This is going to be very important in our next set of problems, because we're going to be rationalizing the denominator of some of these fractions that contain complex numbers, and we're going to be using this trick. So this is how we're going to be rationalizing in a minute. So make sure that you can do these before you proceed. Okay, when it comes to dividing complex numbers, you're not dividing in the traditional sense. There's not going to be any long division or anything like that. You're basically rationalizing the denominator. So if the denominator is a simple I, such as the case here in the first one, then all you're going to have to do is just go ahead and multiply that by multiply it by just I over I, because notice what happens. You end up with -8i over I squared, and we know that I squared is -1. So right there we went ahead and rationalized the denominator. There's no more radical in the denominator, because remember, this right here contains a radical in the denominator, because after all, what's I? I is the square root of -1. And remember, no perfect squares and no negatives left under the radical, any radical, and no radicals in any denominator. So we're dealing with this part right now. We're making sure we get rid of any radicals in any denominator. All right, and of course, -8 over -1 is just 8, and we just end up with 8i. So that's how you handle something like that. Now, if you've got two terms, however, notice multiplying the denominator by just an I, let me try it down here, isn't going to do the trick, because if you distribute that, you end up with I minus 6i squared. This part is -1, so you end up with negative times negative is positive. You end up with 1 plus I. You still have an I left, so that's not going to take care of the problem. So what will is what we just noticed in the previous screen. So with something like this, we're actually going to multiply the numerator and the denominator by the conjugate of the denominator, because it's the denominator that we're trying to rationalize. So we multiply times 1 plus 6i, 1 plus 6i. Now we're just going to go ahead and multiply the top. That's just going to give us 2 times 1 plus 6i. I do not recommend distributing that already because we may be able to do some cross-canceling later. So it's always a good idea to leave that until the very end. And then over, of course, 1 minus 6i times 1 plus 6i. If you remember from the previous screen, here f is 1, L is 6i. So you're just going to get 1 squared minus quantity 6i squared. And that's what we write. So we get 1 squared minus quantity 6i squared. So now we have 2 times 1 plus 6i over 1 minus, make sure that's not mistaken for an I, that's just a 1, minus 36i squared. Of course, we know that I squared is negative 1. So basically, we have 2 times 1 plus 6i over, notice that this negative 36 times this negative 1 is going to give us plus 36. So 1 plus 36, that's 37. Now I notice there is no cancellation possible, so it's safe for me to go ahead and distribute that 2. So I get 2 plus 12i over 37. But I'm not going to leave it like that because remember, we always want to put it in standard complex form. So we'll just go ahead and write it as 2 over 37 plus 12 over 37i. And that's how we leave our final answer. Okay, so as you notice, it's not really division in the classic sense. It's more of rationalizing the denominator. All right, so finally our last problem. Yes, huh? Okay, so we're going to use the same trick. We're going to rationalize the denominator. Do yourself a favor, pause, do this on your own, then come back. All right, we'll come back. So now we're going to go ahead and multiply the numerator and the denominator by the conjugate of the denominator. Remember, it's the denominator we're trying to rationalize. So by 4 minus 2i, and when we do so, we end up with 4 plus 10i times 4 minus 2i on the top, and we end up with, remember, product of conjugates is the difference of squares. So 4 squared minus quantity 2i squared. And on the top, you can go ahead and just do it horizontally, or you can use a table. Let's just do it horizontally this time. So we'll distribute the 4. So we get 16 minus 8i. Now we're going to distribute the 10i. So we get plus 40i. And then 10i times negative 2i will give us negative 20i squared. Downstairs we have 16 minus 4i squared. All right, we know that this I squared is negative 1, and so is this I squared. So when we go to the next line, we'll keep that in mind. So we have 16 This negative 20 times this negative 1 is going to give us plus 20. Let me go ahead and put that next to 16 because it's like it. And then we have minus 8i plus 40i. On the bottom we have 16. Notice negative 4 times negative 1 is going to give us positive 4. So we end up with 36 plus 32i over 20. And of course, we should go ahead and split that up and put it in standard form, which is 36 over 20 plus 32 over 20i. Being a math class, we're always going to reduce all our fractions. So 36 and 20, we know they have a common factor of 4, which goes into 36 9 times. It goes into 25 times. 32 and 20 also have a common factor of 4, which goes into 32 8 times and into 25 times. So we're ready to write our final answer, which is 9/5 plus 8/5 I. So again, very simple, but just have to be patient and go through all the steps carefully, making sure you don't make any errors in the arithmetic, and you should be just fine. So we have one last problem hiding in the corner here on the left, which I almost forgot about. But basically, to handle something like this, you're going to have to remember the rule. Let me write it on this side, which was had to do with negative exponents, which says x to the power of negative n equals 1 over x to the n. So we're going to go ahead and rewrite this as 1 over I to the 13. And of course, to rationalize that, I don't quite have to multiply it by I to the 13. Like in this case, we noticed we multiplied by I, so you may start thinking I have to multiply it by the same thing. No, I just need to multiply it by a single factor of I, like this. So now we end up with I over I to the 14. Now we know that I to the 14 we can write as I squared to the power of 7. So that's I over, we know I squared is negative 1 to the power of 7. So that's going to be I over negative 1, which can be written more simply as negative I. Just wanted to go over those negative powers in case you encounter them. So that basically should wrap it up for complex numbers and operations on them. And we will visit complex numbers again once we study quadratic equations in detail. We've only seen some quadratic equations in the past, and they all had very simple solutions, and they never ended up being complex. Now we're going to be encountering some which has complex solutions, which have complex solutions, and we'll be able to handle them. So that should do it for this video. So take care and be safe until our next video.